Okay, hello everyone. Today I'm going to present our work on correlation aware flow consolidation for load balancing and beyond. My name is Shiva from University of Toronto, and this is a joint work with Matt, Parsa, Faraz, and Yashar. So today's network topologies offer several equal cost paths between any pairs of different servers. This makes load balancing an extremely critical component in today's networks. So existing schemes, some of them are random and oblivious to the congestion in the network. So the packet-based ones, the very well-known one is the ECMP, and there are a few flowless ones like Presto, Let Flow, and so on. There are a number of congestion-aware load balancing schemes, such as a local one called Drill and a bunch of global ones like Congo, Hula, Clove, and so on. So the challenge of all these load balancing schemes is the volatile nature of flows. So we have a lot of fluctuations in the rates of the flow during the intervals of these load balancing schemes. And what happens is that due to these fluctuations in the rates, we will see undershooting or overshooting of the link capacities, which is very problematic for the load balancing schemes. And these existing schemes, they are either random or rely on average measurements of rates or congestion in short periods of time, but none of them consider second-degree variations in flow rates. So that's why we suggest correlation-aware flow consolidation, and our goal is to minimize the collective rate variations of flows that are assigned to paths in load balancing. So we suggest to aggregate inversely correlated or independent flows into what we call superflows, and then we feed the load balancing schemes with these superflows. With these superflows, we can enhance the existing load balancing schemes in three different ways. First of all, we can reduce the peak requirements and avoid this overshooting and undershooting of the link capacities. Also, we can have a better estimate of the demands of groups because we are lowering the variance in the group rates. And finally, we can eliminate the congestion in time scales smaller than the control loops of these load balancing schemes. Let's look at a very simple example to clarify this correlation-aware flow consolidation. So here we have four flows. These are generated from four Gaussian process distribution, and flow 1 and flow 2 are inversely correlated, and flow 3 and flow 4 are also inversely correlated. What it means is that, for example, if you look at the two blue flows, F1 and F2 here, when this light blue one goes up, the other one around the same time it goes down, and vice versa. Whenever the other one goes up, around the same time with some randomness, the other one goes down. So this is what we mean by inversely correlated. So here we are comparing two different consolidation schemes. On the top, we can see a correlation-aware flow consolidation in which we aggregate these inversely correlated flows. For example, here we aggregated flow 1 and flow 2 together, and what we see is that these variations in individual flows are canceled out because we are aggregating based on their correlation, and this black line over here, which shows their aggregation, is much smoother than any individual flow and has a very low variance. On the other hand, on the bottom here, we have a grouping based on the average flow rates, which is what many of these existing load balancing schemes do. So they rely on average measurements of rates or congestion. So here, the average rate of flow 1 and flow 2 is 10, and their variance is also 10. For the other two, flow 3 and flow 4, the average is 15, and their variance is 15. So to be best in terms of the average group rates, we want to aggregate flow 1 with one of these two flows. For example, flow 3 and flow 2 with the other one. In this case, the average will be 25, which is best on average. But if you look at these variations or the variance over time, we have a lot of ups and downs. So for example, we have this peak over here, we have this dip here, and what happens is that this will result in overshooting or undershooting of the capacities in load balancing. So let's see how we formulate this problem. We assume we have n flows, F1 to Fn, and these are the flows that are going to be balanced over several paths. And our goal is to consolidate them into k different groups, G1 to Gk. So we are looking for this group function which maps flows to one of the kth groups. And a group of Fi equals k, this implies that flow Fi belongs to the kth group. So here is this is an example of this problem. So we have 6 flows over here. We have 3 groups, and then this time is slotted here. These orange boxes show the time slot, and every t epoch units of time, we want to regroup or reconsolidate these flows to make sure this is a dynamic scheme. And in the paper, we provide an integer programming optimization problem for this. And the goal of the optimization problem is to minimize the maximum of the aggregate rates among all the possible grouping functions. And the goal here is to make sure that this aggregated rates of superflows are not overshooting the link capacities. And we show that the well-known multiprocessor scheduling, which is an NP-hard problem, can be reduced to this problem. So the computational complexity of this one is also NP-hard. And to resolve this computational complexity, what we do is we use variance of aggregate rate instead of the maximum. And also to control the variance of group rates, we focus on flow correlations. Our intuition here is that if we aggregate independent or inversely correlated flows, we can result in less variance for the group rates over time. Another challenge here is a practical challenge, which is we don't have access to individual flow rates a priori. So the flow rates of the future is unknown. So to resolve this issue, we are using a prediction component, which receives the flow rates from the previous epoch, and based on that, it provides some estimation for flow rates in the current epoch. This is the high-level scheme of our system. So as I just mentioned, we have a prediction component. It runs every at the beginning of each epoch. It receives the flow rates of the previous epoch, extracts some stats from that, and using them, it will provide some predictions for the flow rates of the current epoch or for the future epoch. And then this will be given to the correlation aware heuristics, which I introduced in a couple of slides. And then, the responsibility of this component is to group flows into k different groups and generate these superflows, which will be given to the load balancing scheme. So the prediction component here, it's using the flow rates of previous epoch. It extracts these stats, specifically the rates of individual time slots of the previous epoch, the maximum rate, the mean rate, standard deviation, skewness, and the start time of the flow. So these are given as the features to this prediction component. We tested different predictive models, and then using them, we can have some predictions on the flow rates for the current epoch, which will be used in the other components of our system. The first 30% of the epochs are used for training, the next 20% for validation, and then last 50% for the testing. And our prediction metric for the evaluating the validation phase, we use the R-squared. And the reason that we use this metric is that in the data set, we see a lot of zero rates, and that's why this metric is much better here compared to other metrics. So for our heuristic, we tested a number of different correlation aware heuristics, and this one, which we call lowest correlation grouping or LCG, is the one that performed best in most of the experiments. So let's look at the details of this one. So here the goal is to iteratively assign flows into these K groups, such that we make sure that the correlation of each flow with each group is minimum. So we initial K empty groups G1 to GK, and then for each group we maintain an aggregate flow or a representative flow called S of K for each group, which is the aggregate rate over the time slots of this epoch for this group. And then for each flow, we want to assign it to one of these K groups. So we need to find the correlation of this group with each of these representatives or this S of Ks. And then we find the minimum correlation among them, and the corresponding group is called GSR. For example, assume this is the one with the minimum correlation, and we compare the correlation of this minimum one with a threshold. If it's smaller than the threshold, we'll assign F to this group. Otherwise, we'll assign F to the next empty group if there is an empty group available. So for the experiments, we used real ISP data, and used 500 flows for half an hour from this real traffic. We also passed these flows randomly from 30 different paths to make sure that we have some kind of correlation among the flows. And then we compare three different, our heuristic, which is LCG, with two different heuristics. The first one is HRF, or highest rate first, which is inspired from an approximation algorithm for the multi-processor scheduling problem. Here, what it does, it assumes that we have the average rates of the flows for the current epoch. This is an unrealistic assumption, but we just make this assumption and show that with this strong assumption, still our heuristic LCG performs better than this. So we assume we have the average rates of flows in the current epoch, and then sort them in a descending order. And on this descending order, we assign each flow to the least loaded group. And then this random heuristic is simply assign flows to a random group. We compare the mean and maximum group standard deviation among these different heuristics. So here we show the mean standard deviation for assigning these flows to 20 different groups, and we have two sets of experiments. So in the first set of experiments, we didn't use the prediction component, and we want to show how important this prediction component is here. So in the figure on the left, we didn't use the prediction component. We have two versions of our heuristic. So in the first version, this solid line over here, we use the rates from the previous epoch to run these heuristics. And in the second one, this dotted one, LCG using the current epoch, we assume the unrealistic assumption of having the rates of the current epoch, just to show some experiments here, but then later we'll relax this assumption in the next experiment. So here, as we can see, the solid one, which uses the pure rates from the previous epoch, it doesn't perform well, especially here after, like for this 40% of the epochs, it performs worse than even random. So it doesn't seem to be a good solution here. On the other hand, this dotted one, which uses the rates from the current epoch, it is consistently better than random and HRF with a significant gap over here. What it suggests is that if we have good estimations for the flow rates, this LCG can reduce the standard deviation significantly. That's why we decided to use this prediction component, and using this predictive models, we have the figure on the right. And as you can see, this LCG version here, which uses this predictive rates, is significantly better than the other two heuristics, reducing the standard deviation of the groups. Here we run an experiment to to try different number of groups. So we varied the number of groups from 2 to 30. And as we can see, this black line, which is LCD, is always, in the most of the time, it's below this the other two heuristics, which means that we are reducing the standard deviation for all grouping sizes. And as we go further to the larger number of groups, we can see that the standard deviation is reduced, which is much better for the load balancing schemes that are going to use these superflows. To conclude, this is, to the best of our knowledge, this is the first solution for load balancing that considers flow rate variations and flow correlations. It consolidates inversely correlated or independent flows, and it reduces rate fluctuations using these superflows. Our design includes a correlation-aware heuristic for the NP-hard problem and a prediction component to resolve the issue of unknown future rates. Our experiments show that a significant reduction in the standard deviation of group rates can be done using this prediction component in combination with our LCG heuristic. And also the experiments clearly show the importance of this prediction component. As for future work, we want to evaluate the existing load balancing schemes in the literature combined with our solution to see how we can improve those schemes. And also we want to explore other applications beyond load balancing, as we believe this can be useful for other resource allocation problems in networking. Thank you very much for listening, and I'm happy to answer any questions or any feedbacks. Thanks.
Thank you very much, Shiva, for the talk. Is there any question?
I have a question. First of all, thank you for your presentation. Can you get back to the slide showing the how to aggregate flows?
This one?
Actually, just right before the evaluation setup. Right before the evaluation setup slide.
Oh,
evaluation setup slide. Yeah.
Oh, okay.
Yeah, this one.
Yes.
Okay. So here, yeah, it makes sense to me. But here initially, there will be no flow error, right? Initially.
Yes.
Then it's not possible to calculate any correlation at the time, right?
So yeah, for the first flow, we just assign the first flow to the first group because we don't have any flows in the groups.
Okay. Okay. If there's no flow error, then you're gonna choose just like any of the empty one.
Exactly. Exactly. Yeah.
Okay. 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 Great. Then can you move to the evaluation result?
Yes.
Here, right. This shows with the prediction component, it shows the standard deviation is growing, right? In the right side, the standard deviation is much higher than the left one, right?
Sorry, what was the question?
Okay. With rigid regression here on the right side,
yes.
The standard deviation shows much higher than the left one.
Oh, okay.
Yeah. I expected like using the prediction model, the standard deviation should be much smaller, right? But I don't know. I don't understand why it happens. I mean, the indication of the result.
Mm-hmm. Yeah, you're right. Let me think why this happens. Probably, probably the number of groups are different into these two experiments. Probably they are not for the same number of groups.
Mm-hmm. Mm-hmm.
Yeah, I think here the number of groups are decreased because you're right. If we are using this one, we expect that the standard deviation is reduced.
Mm-hmm.
Yeah.
Okay, yeah.
But this is a good point.
Perhaps the reason would be we can find from your paper, right? Actually,
Yes.
if you read the paper, then maybe we can find the answer. Okay.
Yeah, I remember we tested this with different number of groups, and that's my guess as far as I remember. Probably this one is for 10 groups, and probably this one is for 20 groups. Yeah, but this is a good point. Thanks for bringing this up.
Okay. Okay. Thank you.
Thank you.